Welcome to This Explainer. Today, we're grabbing our network architect hard hats and breaking down exactly how device addressing has evolved to keep the modern internet actually functioning. We all use the internet every single day, but rarely do we stop to think about the incredible administrative scaffolding happening behind the scenes just to make sure your data gets exactly where it needs to go. So we're going to look closely at the absolute fundamental building block of that communication. Here is our blueprint for today. Number 1, the logical network address. Number 2, understanding the IP generations. 3, the IPv4 class system. And finally, number 4, private ranges and modern evolution. All right, let's jump right into section 1, the logical network address. To really understand network management, we first need to define the most fundamental tool in an administrator's toolkit. Now, every piece of network hardware comes with a permanent, physically baked-in MAC address, right? But an IP, or Internet Protocol, address serves a very different purpose. It's a completely unique logical address assigned to a specific device on the network. This provides the essential scaffolding for Layer 3 routing, which basically lets administrators systematically map, segment, and control exactly where data packets flow across some pretty complex topologies. When a device requests data, the IP address acts like a dynamic, routable homing beacon, making sure those returning packets find their exact way back through the massive labyrinth of the internet. Moving on to section 2, understanding the IP generations. And guys, this is where the story gets really fascinating, because as the internet absolutely exploded in popularity, we ran into a massive scaling problem. We literally started running out of these critical addresses. The traditional IPv4 architecture gave us a 32-bit address space, formatted in those familiar decimal octets you've probably seen, like 192.168.1.10. And hey, it served us incredibly well for decades. But math is unforgiving. With billions of new devices coming online, we simply ran out of unique combinations. The solution? A massive evolutionary leap to IPv6. This newer standard uses a 128-bit architecture written in hexadecimal format, and it completely reimagines how we allocate space to ensure we never, ever face an address drought again. To really wrap our heads around the scope of that jump, we have to look at the numbers. By upgrading from 32 bits to 128 bits, administrators are provided with roughly 340 undecillion unique addresses. Yeah, undecillion. To put that completely unfathomable number into perspective, that is more than enough routing space to assign an IP address to literally every single atom on the surface of the Earth. It totally future-proofs our global networks, guaranteeing that every smartphone, smart fridge, and server can have its own unique identifier forever. Which brings us to section 3, the IPv4 class system. Because long before IPv6 came along to save the day, network administrators had to be highly organized with the limited IP4 addresses they actually had. In the early days, they relied on a really rigid, hard-coded blueprint known as the class system. The absolute workhorses of this system were classes A, B, and C. They effectively portioned out IP blocks based strictly on intended network size, so they distribute vast swaths of addresses to massive global corporations while reserving smaller, tightly defined blocks for localized setups. Meanwhile, classes D and E were cordoned off entirely for highly specific tasks, like multicasting traffic to multiple points at once, or reserved strictly for experimental engineering research. The true beauty of this rigid classification was that it basically served as an administrator's cheat code. Literally, by checking just the very first number, an engineer could instantly grasp the underlying network architecture at a single glance. Spot an IP starting with a 10, boom, you immediately know you are dealing with a massive Class A network. See a 192? That's a standard small Class C. It provided this universal language for navigating complex digital environments with extreme efficiency. Now, nestled right between Class A and Class B is a highly specific reserved block, the 127 range. This entire block is dedicated exclusively to a special diagnostic function called loopback. The most famous example is 127.0.0.1. It allows a device to communicate directly with itself without sending any data out over the physical network. It's such an essential local testing tool for administrators that it spawned the classic IT joke, there really is no place like 127.0.0.1. Gotta love a good nerd joke, right? All right, let's move into our final section. Private ranges and modern evolution. We're going to see how all of this builds into the modern networks you interact with every single day, whether you're sitting in your living room or at a desk in a huge corporate office. So, to further delay that impending IPv4 exhaustion problem, network engineers introduced RFC 1918.
This critical document explicitly carved out private IP ranges that would never, ever be routed on the public internet. By designating specific blocks within Class A, B, and C as private, it allowed millions of completely separate networks across the world to safely reuse those exact same addresses internally. The magic that makes this possible is NAT, or Network Address Translation. It essentially acts as a gateway, letting all those private internal addresses share a single public IP to speak with the outside world. But here's the thing, network administration never stops evolving. Today, those rigid Class A, B, and C boundaries are largely considered legacy systems. They were brilliant for their time, for sure, but highly inefficient. Handing a massive Class B network to an organization that only needed a few hundred addresses was just a huge waste. Modern network administrators rely on CIDR and subnetting. This approach abandons strict classes entirely and instead uses a slash notation, like /24 or /26, to visually indicate exactly how an engineer has carved up the IP range with mathematical precision. It ensures highly flexible and efficient allocation. And that leaves us with a truly fascinating thought to conclude this explainer. We've seen how we stretch the absolute limits of the 32-bit IPv4 system using rigid classes, then private ranges, and finally, the flexible precision of CIDR. But as our technological blueprint rapidly shifts to the 128-bit vastness of IPv6 to handle unimaginable global scale, what completely new tools and protocols will the next generation of administrators need to invent? How do you even manage a world with trillions of uniquely addressed, constantly connected devices? I hope this deep dive has given you a newfound appreciation for the incredible architecture keeping our digital world linked together. Thanks so much for joining me on this explainer, and keep asking those big questions.